sometimes it's helpful to break down vectors into their components, meaning like xy or xyz if it's a 3D vector. So in this example, we're given this vector f. Let's say it's a force, and let's say this force here has a magnitude of, I don't know, 10 newtons. Okay, so 10 newtons of this force. And we want to know what is the component in the x direction and what is the component in the y direction. So if I draw that, we're looking for the vector here in the x direction. So that's fx. And then also in the y direction here, which is fy. Okay, so if you remember from geometry, the cosine of an angle, right? If this angle is given as 30 degrees, we have the cosine of 30 degrees here is the adjacent over the hypotenuse. So if we have this triangle here, we have the adjacent, which is fx, over the hypotenuse, which is the magnitude of f. So I'm going to write the magnitude of f as this vector with two lines here. That means magnitude. And we know the magnitude of f is 10 newtons. So solving this equation here for fx, we have fx is equal to 10 cosine 30 degrees. All I did was move the 10 to the other side here. And if we want to figure out fy using the same geometric principles, sine of this angle 30 is opposite over hypotenuse. So fy comes out to be 10 sine 30 degrees. Okay, so that is our components in the x and y directions breaking down this vector f. Now we can write that in Cartesian coordinate form. Okay, so if we want to represent f in x, y, z components, we can write that as f is equal to 10 cosine 30 degrees, and that's the x direction, so we write an I here. And then we have 10 sine 30 degrees. And that's in the j direction. And I put these little hats on these because these are vectors pointing in those directions. So we say that I is equal to the x direction, j is equal to the y direction, and likewise k is the z direction. So these are components in the x and y directions here, and this represents this vector. Okay, so sometimes we're given vectors already in this Cartesian form here, and we don't know the magnitude or the length of those vectors, and we want to be able to find that magnitude. So if we're given a vector in this form, right, let's say we're given a vector A is equal to AX in the I direction plus AY in the J direction plus AZ in the K direction. So these are all numbers. You can think of AX, AY, and AZ as numbers, and these are the directions here. So how do we find the total length or the magnitude of this vector? Well, it's nothing more than the Pythagorean theorem, right? AX squared plus AY squared and AZ squared, and then we take the square root of that. All right. For 2D problems, AZ is going to be equal to 0, right? So we would just leave off this AZ part and set that equal to 0. Okay. So that's so we went over how to break a vector down from its magnitude and angle to its components. And then we also showed if we're given the components of a vector in Cartesian form, how do we find the magnitude? So that's going one way and then back the other way. We can do both of that. Sometimes in problems, we're given things like this. We're given the vector A, and then we're given kind of the rise and run of the vector. So I'm going to put a 3, 4, 5 triangle here, all right, on this. So if we want to break this into its components, right, fx, or I should say ax here, ax is equal to the x direction. So you see that this 3 is in the x direction here. It's 3 over the hypotenuse, 5, times the magnitude of a. So 3 times 5 times the magnitude of a represents the x direction. Now if we want to do the y direction, ay, right, we use the vertical component of this, which is 4 over the hypotenuse, which is 5, times the magnitude of a, all right? So that's how we would, if a vector is given in these sort of, in this sort of notation, this is how we break it down to x and y components. And that's a brief lesson on how to break vectors down into components.